everyone, and thanks for joining. My name is Aurelian. We're going to talk about enterprise architecture a little bit today. So, I'm a Java lead developer. I've been programming for 15 years now in multiple languages. And in this past time, I have been implicated in numerous projects where I also had the opportunity to contribute with ideas for the enterprise architecture, transform it into reality, mainly by applying a software design that reflects all of those ideas that I gathered along the way and that solves cross platform issues alongside making sure the applications I had worked on are secure mainly. Today, we're going to talk about some architecture practices and common pitfalls, most of which I have encountered along the way in these years. And the plan is that by talking about some real use cases, we will try to figure out together a process of coming up with solutions, how deciding a single one should go, as well as trying to avoid common issues mainly. Today's main mission is to figure out who does what and if we should get involved, how we could do that, and what would be a good practice and process of taking a decision. Because we might have, and we always do have, multiple stakeholders into the decision making, and it generally isn't a one man job. The objective overall is to improve platform stabilities on the projects we're working on, and also security and other technological aspects and solution design. First, we're going to talk a little bit about the creative process, and we'll start elaborating from that. Architecture and development both are a creative process, but they are also abstract. They can have an abundance of solutions for the same problem, like we're already used to. Just like any other art form, it requires proper use of technique and knowing the intricacies of the tools we use. What matters is that we get involved and try to understand the needs of the platforms we're working on, create a culture of practices, help solving at least the issues already discovered by others, just by keeping ourselves informed. So now, into comparing architecture with software design, I will start by saying that by definition, software architecture is the process of converting software characteristics, such as the ones we see on the screen, into a structured solution that meets the technical and the business expectations. While software architecture is responsible for the skeleton and the high level infrastructure of a software, the software design is responsible for the code level design, such as what each module is doing, right? The class scope, the functions, purposes, packages, and so on. Yet, if we look at the terms, we see that although the enterprise architect can suggest into detail how we could obtain that, it comes down to developers to take care of things like scalability, for example. If we talk about security and take a simple thing like a GVT token, one thing I encountered was missing to validate the GVT signature, right? So GVT being a security authentication mechanism, right? A token we send to say who we are, and validating who is the issuer is a very, very important aspect that doesn't happen by default. So looking into that before reading and using the claims, which means we are secure in terms that we close our endpoints and require GVT, but in reality we accept any GVT from any issuer. So the entire approach is in fact designed and executed by the entire team, and maybe also most of the time multiple developers that work on the same full feature, which means we are as good as our weakest link, and thus must all know as much as possible about the business domain and the technology details. We will see later on what happens when introducing a single flaw and how it can become a single point of failure for the entire system. We often find ourselves talking about the comparison between monolith versus microservices and start off with the question, which is better? We should also keep in mind that the comparison is not between technologies, but it should be pros and cons, advantages and disadvantages for our specific use case and application. Just like, for example, we heard Victor a lot about talking this comparison between pros and cons, which I really enjoyed. So both are good given the right context, and we look into this context while also thinking about how we can use all of this in our advantage, because they do both have a lot of advantages that we could use for our sake. So looking a little bit into the monolith pros, we know that it has a single deployment artifact and a single code base, right? So it's a good starting point for new projects, for example. It's easier to manage that code base initially until it gets big at least. It's simple to develop, test, deploy when small again, And cross-cutting concerns and customizations are dealt with only once, meaning that if you do session management, login of the user, or other cross-cut aspects that go on the vertical of our platforms, in Monolith you do it only once, so you don't reinvent the wheel over and over again. Looking at the cons a little bit, business logic is tightly coupled with the entire application. So it might just be that if we let it spread it out, doing a single simple change could be a real headache. The build is slow, especially when it becomes a big artifact. It's harder to understand and to onboard, meaning that bringing new developers uh, mm, to work on new features and continue beyond maintaining just the application would be a headache. And continuous integration is hard to implement and start time is longer. So these are a couple of things that would hurt us when working with big monoliths. Looking into microservices, just a couple of facts. Of course, these lists are could be so cumbersome, and so many points could be added. Reliability, as one failure doesn't break the entire system. Mainly, if you have a system go down, a microservice go down, from a flow that we might not even use for a couple of minutes. This doesn't break the entire ecosystem, right, of our platforms. It's more agile as team members can work in parallel. So we could have different teams working on different services, just like most of us are already used. Better scalability because these services are so small and dedicated to a single business domain that we could scale it up on different platforms and into the cloud. And technology independence, one out of which I like the most, and faster onboarding. Technology independence because mainly each microservice can just be developed in any language you together without any issues. The cons of the microservices, they're harder to maintain, especially initially. So if you just start up a project, if you start 10, 15 microservices, that doesn't help you very much because you would have to develop a flow into all of them, maybe, or quite a few. Possible cost issues to scale. So I think we should start thinking about costs of introducing technologies and things we work on, because on the high level design, on the bigger scheme, it's pretty important. On the how do we approach this network latency, because maybe for a single user profile to be loaded, we make 10 20 calls, who knows, and we might reinvent the wheel with cross-cut concerns, meaning that if you have 5 microservices, for example, each of them required mechanism of authorization, you could have developers implementing them in different ways, introducing new bugs because they are again and again doing the same thing, which also implies costs and time. So one good aspect would be having them working together so that they develop a single solution for these cross-cut concerns and then use on the entire platform. We're going to look a little bit into what would it mean to start with a monolith and plan for a microservice. So how could we approach this? How they could fit and work together for our advantage. We're going to look a little bit in an application that's developed with Spring and Java, and we also have here Maven. In front of us, we see the POM XML from Maven for a Java-based application, as I was saying, in Spring, that has a monolith structure and the parent POM XML on the right side with multiple children applications, but structured on business domain, like we're used to when we see microservices. So what we see on the left side, we have here a couple of Maven modules like DMS, events, EDP, and so on, all structured on business domain. So what I like most that we have things like organization, subscription, and also the firm's events, for example, in a microservice, but also technical aspects like a common library or document management system or identity data provider like this EDP. So we start off with a monolith, we put them based on business domain, and later on we can start pulling them out of here into independent services. On the right side in the POM XML, we see the parent definition first. We have the packaging, where here is a little bit different because the packaging is a POM. It's not a jar artifact anymore. And below we have the modules declared, like all of them that we can see on the left side. Now, if we look in the same POM XML of the parent, we see that we don't have dependencies, but dependency management. So this is also a great way to structure our microservices and decide on the tech stack they use, make sure that they all have the same versions of applications, same versions of Spring, for example, and we decide in this parent POM what to use. Below, we see for Spring Boot Starter, Spring Security, we have the version here, which comes from properties, but also some dependencies that come from the same project. So what does this dependency management does? It doesn't import anything for us, but it just puts out there what we should use in the children and what should be made available. Now going into a child module, in front of us here, we see we have dependencies. On the top part, we identify the parent, which is the main POM XML. And in dependencies, we can use other structures, other packages and modules from the same application, and we just need to mention the version, which is the project version. And below, again, a thing I like the most, so as I was saying, we have the Spring context, but no version mentioned, because like this, all children will take the version from the dependency management we introduced in the parent POM XML. Like, as a small conclusion, so we start off simple and we plan for the future, basically, right? Now, we're going to talk about some practical, more complex use cases for 3 more projects, and we will investigate ways of analyzing the requirement from all angles so that we can figure out which are the viable solutions. Project number 1, described here, is about a trading application that had a C# desktop app, but with a Java backend. The trading application needs fast and high load throughput when communicating with the Java app, but also with other third parties after the Java backend. The main requirement is achieving a reliable and fast communication with the Java processes, right? So the concerns would be interoperability between these technologies, low speed, loss of data, which could cause trade loss, which would be the worst, of course. As well, consider that both applications previously existed but didn't interact before. So when talking about solutions, the most obvious would be merging one into the other and having a single monolith application, like we see on the left side, right? But the main drawbacks are cost and time related, because there is a lot of business logic in both that would take a lot to rewrite. So IKVM or JNI, as we see in the middle, right? IKVM is a software that uses RMI to create a bridge between the technologies. This was also considered. And Java Native Interface, JNI, that we see there, creates a bridge between the bytecode running in our JVM and the native code, which usually is C, C++. The side effect when thinking about these solutions was that we figured that RAM should be used for fast communication, like we see on the right side. So mainly, we should put both of them on the same machine. For conclusion, the most obvious one is that there is no single viable solution. Development team needs to be involved in the planning in order to address the level of expertise required to implement any solution, and of course possible technical drawbacks, right? Because before being able to decide on such complex technologies, we need to understand them better. Maybe we don't have any team member that has worked with these technologies. This doesn't mean we should exclude them. We shouldn't keep ourselves just by working with things we're familiar with, because we might have other technologies that perform better. So instead, we should have workshops, proof of concepts, try to figure out together which are the possible solutions, and then benchmark them and see how it goes, which one is the better, and start documenting ourselves and learn about the solution. The next use case, the one we have here in front of us, we investigate the TIBCO application. We can say, for those that are not familiar, TIBCO is a middleware. However, there are some presentation layers, some components for the presentation layer that exist within TIBCO, right? So it's an enterprise application integration, EAI, which promotes service-oriented architecture. The major portion of its implementation is in Java. The TIPCO application, in one of its flows, had a custom plain Java library that had to process a big Excel for the final output. So, like we see here on top, the TIPCO application is a conglomerate, right, of processes, and somewhere within we had the Java, plain Java library that was supposed to process this file. The main requirement is to fast process this Excel file that might reach 100,000 rows. Yet the cause of concern was that at random times, the file processing takes longer than expected, ranging from 12 seconds to 100 seconds in production. So, looking a little bit into the main problem, what we know is that all the application and libraries are deployed on the same platform, which in turn causes a race for CPU and memory, which eventually makes processes fail or stall because they're waiting for the garbage collection and the CPU. So all of this is due to the fact that the Excel is loaded into the memory entirely, which brings the heap to consume most of the allocated space. So if we think a little bit about solutions and how we dealt with it, the first proposed solution was obvious. Why don't we make the calls asynchronous? So like we see here, this dotted line. So why does the user in the GUI, in the GUI, should wait for the response? This was the first thing that we thought about, and it was a great opportunity to think if we really need the UI to wait for the response on this processing. It seemed that there was some validation, as I was saying, and this meant that it impacted the user experience if we changed that approach. So what could have been done was making the call async and checking for validation later. Another open topic was to increase the resources on TIPCO overall and also the heap, but the race would have continued. So we could have also migrated to cloud and Spring, for example, to achieve service independence and easy scaling. But we had to support the costs of infrastructure and development time. So, like we can see on the right side, only that process could have been moved as a microservice, maybe into the cloud as a Spring Boot application. We could have refactored the code alone. This would have been a solution to bring some improvement and reduce heap usage, but infra issues would have remained, and this might take the longest time to implement. As a conclusion, mainly, again, pros and cons only. So do not prefer any pattern or technology. We need to consider benchmarks and performance analysis. How we also did it in the teams I worked on, we did workshops and proof of concepts to address these technologies. We should also do a case study on what we don't know about the used technology so that we can have a comprehensive knowledge about the underlying layers, details, right, before using them. So benchmarks are a savior always. That's why we can also find a lot of them already for different tech stacks on the internet. Now, as we were discussing about synchronous and asynchronous calls and how we discussed about that decision and possible solution, we're going to look a little bit into how to do that in a REST API, in a microservice that's done with Java and Spring, because we know we have solutions like JMS, for example, in queuing, or we could use Spring Web Flux for this asynchronous requests. But I think it's very important to know that with what we might already have in our projects, we could achieve the same thing without changing technology. So I think this is also an approach worth mentioning, that we should first make sure that what we have in front of us can't already solve the issue. So what we see here is a controller with two endpoints, a post request to start off the asynchronous process, and the get request to read the results. This uh, behind it, it has an architectural pattern called post redirect get, often used in web pages when we create a resource and we don't want the user to refresh the page and recreate the same resource over and over again, or maybe in payment applications where we want to move the user away from that post request. And of course, when the response and the details about our execution lay somewhere else. So in this post request in front of us, we call service in our Spring application, and then as a response, we provide the status see other, which means you should check on another location to find out the results of what you're querying for, of what you executed. And in the header, we provide the location, which is a relative path to where you could find this information, where you should do a GET request. Most of the clients, even Postman, as we will see, automatically redirect to that GET request, the web browser as well. On the GET endpoint, we see another call on a different method in the same service, online here with get demo async, for example, and it returns a future. So this is how we see what happened on that background thread, because this async request will be mostly a background thread that starts the execution that we need to poll, and we need to read from it to see how it went. So it checks if it was completed, and if so, it gets the result, which will be a string in this case, and prints it out. Now looking a little into the service, we have here first our async method. We see it takes a parameter, which would be a thread pool executor. We can skip this, so this is optional, and not provide one, and it will take the main thread pool executor. So if we want a separate one for our async processes, this is the way to go. We'll look a little bit into how we could configure that as well. Our method sleeps for 5 seconds, and then instead of providing the result, it puts it in a shared placeholder, which is a concurrent hash map here, mostly just to show that we can have a distributed mechanism, because when we would scale the application, we will need the nodes to communicate between themselves and discuss about these results. So in this case here, our concurrent hash map could actually be a distributed queue. So a standalone microservice, something like Hazelcast, for example. So we could have a standalone microservice that would handle the inter-node communication in this case. So it just puts the results somewhere in a distributed mechanism, and then from there, with the method below we have here in get demo async, this is not asynchronous. This just checks if for the given ID there was some result printed out there, right? So if it is, it takes it, it removes it, and then prints the result. Now looking a little bit into the configuration, we have here this thread pool executor just to show that we could provide a new one, and we could configure it however we wish. And an important aspect in Spring, we need to enable asynchronous operations like we did just before the config. So there's an annotation especially for that, right? Looking into Postman now, we see here that we made a post request initially. On the bottom right side, we see that the initial post request got a 303 response. So this is the status code for see other. It's a redirect status code. And then immediately it made the get call. It was redirected there. The response we can see here in the body, there was no result yet. And then when polling for the result, making multiple get requests that we can see take only 50 milliseconds approximately, at some point we get the result. So although the background task took 5 seconds for the interface, all the requests were not frozen and blocked waiting for a response. So we could achieve these mechanisms also with what we already have with our microservices based in Java. So now going to project number 3 and a little bit into security issues. Project number 3 is about a car share application that had some security flaws, leaking UIDs, which eventually, as we will see, led to providing unauthorized access to user accounts. So this was an issue discovered by a white hacker doing a security audit at Uber, and which was made public afterwards after they got to fix the issue. So its APIs are made available, and a lot of APIs that we construct and provide are made available for all third-party integrations. So having them public has some major security concerns, right? The main concern is restricting access to data that's not intended for public use. When exposing our APIs, we must always have in mind object level access control in the backend mostly, right? So as well as obfuscating to a minimum of required information. Even if our APIs have ways of providing a more verbose response, we should start with the minimum. Again, this is a good example of awareness, where maybe one developer isn't aware that the UID can be used on a different endpoint he didn't implement to obtain that user access. So it seems, yet again, we need to know our application as a whole. So now getting into what could have been done to avoid this. The main idea is that the hacker could have asked for some user details, like we can see on the top right part. He made a post request with a phone number, but instead he received users information stored with the user's UID. So we shouldn't respond with more than we were asked for, right? So here he now knows that a user exists. So for example, there are things like do not even show that a page does not exist, do not provide the 404 if on an API as a response, for example, if the user is not authenticated, so it doesn't have a token, you just provide the 401, so which is unauthorized. Here again, it was some extra detail that was not needed for this request. The same if you queried for an email, you would have found information that indeed the user exists. So there is a user there, which we're not supposed to say if the query, the person that's making the query doesn't know. We shouldn't give him so much detail. We provided the UID, and then in the final post request, he was able to send this user UID to gain access to all of the user information details like refresh token, address, and so on. But mostly the refresh token was the bad part, because he then, with that token, was able to obtain access for in their names into their accounts. So as conclusions, I think we need to secure the system, right? We should secure the ecosystem, not individual platforms. This means we need to know what the entire application does and how it behaves and where we should expose information. So we should compare input parameters versus output parameters. Do we intend to provide a more verbose response? For example, as seen, the query was with phone number and the response was based on UID. How is the data that I'm providing used? Is it confidential or sensible in any way, like the refresh token? Because maybe we can segregate that data from the response. We should always use the need to know principle. Even on the data we might not seem sensible, the need to know principle should be used. So now, in terms of security, we will address a couple of common issues like data leakage, as we just saw. So this should be considered any part that is not used immediately, not intended for the caller to use, basically, or is highly sensible as it provides access capabilities on other parts of the application. If we talk about Spring security and annotations, if we intend to use annotations from any framework or library, we should make sure that we understand the technologies to a low level, even what are the defaults of that library or annotation, right? Because that can introduce a lot of problems. Introducing backdoors, maybe use some switches to enable disable functionalities intended only for dev environment. This can be used as exploits later on if a hacker gets access to the code base. So make sure you want all that runtime logic in your final production application, basically, if you want all those dev switches. The passwords stored in clear, exposing our passwords maybe even to a lower bound environment, might provide the means to test our exploits if somebody would find that information or how to access the environment, right? So if you have a single service, when talking about securing each microservice, for example, if you have one entry point into the intranet, into the system from the public domain, and all of the other microservices are in the intranet, you might think you would be safe to have them open and you don't have to secure the microservices in the internet. But if you have an exploit in a single service, that would mean that gaining access to one would actually implicate getting access to the entire system. So that's why you should think about this. So understanding JVTs and the tools that we use as comprehensive as we can. Common mistakes in regards of tokens are to expose them unnecessarily. Think about Facebook and Yahoo when they lost millions of user accounts when exposing refresh tokens, just like you saw in regards of the Uber application, right? So it's very easy to expose this sensible tokens in places that we do not actually intend to do that, right? third-party security risk, which implies you must understand how it works and also monitor it. So when you introduce a library, a third-party library, you need to monitor it and see what happens. Even if we think about the global context right now, there were some people, for example, that change on purpose their libraries to destroy computers and systems throughout the world, which initially were used by a whole lot of people that are not even implicated. So a normal library could change its purpose immediately. So we need to check on that. Checking out the latest example, which is log4j, and the way access could be gained through this library. And maybe we should not reinvent the wheel and make sure our security implementations are generic so that all the applications in our ecosystem could use and enhance. Talking just a little bit before I sum up about the single point of failure. So we have here in front of us a complex system with microservices, payment third parties, IDP database upstream with the core components. On the bottom part, we have the continuous integration tools, versioning repository, our dev host, and even our wireless connection, which is very important. And on the left side, we have a mobile and web app that communicates through by JSON to a proxy service that's in front of the intranet. So we have here a small list of multiple ways of providing a single point of failure. So if we, for example, secure only the client side or only the service side, we could have that security bypassed and maybe leak some information. If we secure only the proxy and not the microservices, as we said earlier, we could have exploits on a microservice that provides access to all of them and the entire system. Unverified payment response is something that I saw along the way. So somebody makes a payment, but the application does not wait and check for the response. It just redirects to the success page. We could have an unsecured dev network. We could be on a public Wi-Fi, and somebody can sniff and spoof our requests and gain access to things like our SSH key, which we could use on the versioning repository, and he can see the code and then figure out exploits. Or even worse, we could use that SSH key to access the dev environment or some upper bound environment. We could have the same key for all of them, which of course is very bad. So talking about a single point of failure, we are as good as our weakest link. That's what we should get out of this mainly. Now, thank you very much. Basically, this wraps it up for me. If you have any questions, also feel free to scan the QR here. You can find all the slides. And later on, if you want to pick up on this conversation, you can do so at my email address. So feel free to send me an email.